Is it?
I've just started, Riccardo.
Okay, perfect.
Hmm.
Thank you. Okay, so let me share the screen, and we are. Oh, sorry. There is. Okay. So are there questions on the previous part? Something that you want to see again? Speak or write in the chat? Are there things that you want to see about the Qiskit or algorithm, Grover, and so on? If not,
a general question, if I can.
Yeah, sure.
So is my understanding then that these are the only types of algorithms that are available right now, and everything is based on this kind of approach, or?
Okay. No, these are like the old school algorithm that came up in the 90s. Okay, so these are the algorithm that started all the field of quantum algorithm. Okay, so but still these are the basics and very important to understand what can do quantum computation. Right now, we're going to see it not tomorrow. Or better, tomorrow, Daniele is going to talk about quantum annealing, which is a different kind of algorithm, let's say, which is much more, let's say, with which, let's say, which is less powerful somehow, but with which you can try to solve problems which are almost real world problems nowadays. So the problem here is that this algorithm, and is also a part of the topic that of this of the next hour, is that this algorithm need large-scale quantum computers. So in order to have if you want to use quantum computing in the next 5-10 years, it's very unlikely that you are gonna use this kind of algorithm here that we have seen today. So, but it's gonna be different algorithms that do not require error correction and that are, we say, NISQ ready, which means which are ready to be run on the devices that we have today, which are noisy and of intermediate scale quantum devices. But it's going to be the topic of the fourth day, so of day 4 of the quantum of this introduction. So today, what you've seen are just the old school, let's say, the old school algorithm that came up in the 90s that started everything. Okay. So okay, let's go on maybe with this part. We're gonna understand more. In short, the short answer to your question is no. These are not only the only algorithm, and actually, it's there are many more that are more that take into account the fact that we don't still have quantum computers that are large scale and error corrected. Okay, but we're gonna see it in the next few days. So, okay, as I told you, okay, very briefly, because we just have 1 hour. In quantum computing, there are many sources of errors that can compromise your computation, your quantum computation. These are some examples. Coherent quantum errors, for example, gates that are incorrectly applied. For example, you want to apply X, but this doesn't happen, or the fidelity, which means the state after the X is not exactly X, it may be something else, or after the other mark, okay? Coherent quantum errors. Then there are environmental decoherence, which means error due to the interaction with the of your quantum system or qubit with the external environment. So one example is, for example, IBM or also Google, they have quantum computers of 50 qubits, okay? Qubits are, as Daniele said, they are built using superconducting circuits, okay? And they have to be very much isolated from the outside world, okay? That's why they cool them down to temperatures that are few millikelvin above the absolute zero. So they have to be completely isolated in order to work coherently, I mean, in order to show a quantum behavior, okay? And environment is something that distracts this quantum behavior, okay, of your system. And of course, introduces errors in the computation. Then there are also initialization errors. For example, you fail to prepare the initial circuit, so it's not in the 000 state, it's not in the +++ state, it's something else, no? And then qubit loss. It may happen sometimes that especially if your quantum computer is made up of atoms or ions, and a single qubit the state of a qubit is encoded in the energy levels of your atom or your ion, and then it may happen that your optical trap that traps your ion, which means your qubit, works somehow. So something happens to the trap, and you lose one atom, which means you lose one qubit during the computation. So it may happen also this kind of things. Okay, then let's go on. So classically, there are also okay, probably that's a joke. Classical, so there are error correction, classical error correction, which employs redundancy. Okay, so redundancy means that you store information in multiple times and just take the majority vote if these copies are found later in disagreement. Okay, so classically you have one bit, and you encode it, so 1 bit into 3 bits. Okay, so the 0 bit is actually when you have 3 bits that are all 0, and the bit 1 is when you have 3 bit 1. So basically, if you assume that the probability of error is low, 3 is fine, because the probability of having one error in 1 qubit, the probability of having more than one error, like in this case, the probability of having more than 1 bit error is very low. Okay. So in quantum error correction, we can also use this concept of redundancy to perform quantum error correction. However, there are some complications with respect to the classical case. The first one is the no cloning theorem. What does it mean? It means that you cannot, we're going to see it later, but we're going to see you cannot copy a quantum state into another quantum state. Okay, it's something that classically you can always do it. So you have a string, and you can copy and paste something else. Okay. Then the second complication is that qubits are susceptible to not only to bit flip errors, like the classical case, but also to phase flip, so there are zeta errors. Then the third complication involves a measurement, because as you know, measuring the state involves disturbing the state, so which and measuring, if you want to detect the error, you have to measure things in a clever way in order not to compromise, in order not to collapse your original state, and so not to compromise your encoded your quantum information that is encoded in the quantum state. Okay, so you have to be you have to pay attention to this part, to the measurement part. Okay, so as I anticipated before, this kind of algorithm, like Trover algorithm or Shor algorithm, which are the old school, so the very famous algorithm that came up in the 90s, which provide exponential or quadratic speed up, are actually assume, so the algorithm, so which are great on paper, as we've seen today, this algorithm assume that the qubits are either qubits that are working perfectly and they're not subjected to noise or errors. In order to run this kind of algorithm on large scale, which means on real world problems, you need error correction. So you need a quantum computer that is fault tolerant. In order to run this algorithm on quantum computer with error correction on problems that are real world problems, which means for sure, for example, factoring a very large number, this means that you need thousands and even millions of qubits. Okay, because error correction with the redundancy, as you can see on the left, increases, so you have an overhead in the number of qubits. Okay, these kind of devices that are large scale and error corrected will be available. The forecasts say that they're going to be available in 10, 20 years. Scientists predict that it's going to be 10, 20 years, more or less. Okay, hopefully. However, how how error correction works? So again, today the focus is on algorithms that may work with computers that are not error corrected, but which do not have like strong mathematical proof of their speed up or about their performances. But so today the research that is going on is basically on this topic. Okay, understanding what can quantum a quantum computer that is not error corrected, what can this kind of device do? However, let's forget about this and focus on error correction. Okay. So again, the concept of redundancy, Noetherian theorem, and correcting errors, and taking into account the fact that measurement affect the quantum state. So these are the topic of this last hour. First of all, the cloning theorem. No cloning theorem, I mean. The cloning theorem states the following. So states that it does not exist in an universal cloning machine, which is a unitary transformation or an operator, such that when U is applied to a state psi, the state that I want to copy, and alpha, that is a state that is blank, so that where I want to store the copy, so that acts like this, so generate in a state that was previously alpha, the new version of psi that is exactly equal to psi, a unitary of this kind does not exist, okay? For every psi and a fixed alpha, okay? Why this is not possible? And we have the mathematical proof that it's quite easy, okay? And the proof goes by contradiction. So suppose that such universal cloning machine, so that such operator exists, and apply it to two states like below. I mean, like here, like shown here. So we apply the matrix, the operator U to the state psi1 with alpha as a blank in order to obtain two copies of psi1. Same thing, we do it with the psi2, which is a different quantum state. And we apply it, we apply the U in order to get a copy of psi2. And let's go on. And consider now the scalar product between the terms of the equations. So which means we consider the scalar product of this term with this term on the same side, and the scalar product of this term with this on the same side, okay? Scalar product means you are complex conjugating and transposing this part. So you are doing the adjoint of this part. So what you get is the following, okay? So you get this term for the left-hand side and this term for the right-hand sides, okay? But then if you look closer, since U is unitary, U dagger U is again the identity, this scalar product becomes the scalar product of alpha times the scalar product of psi2, psi1. While in this other case on the right-hand side, you get the modulus, you get the scalar product 2 times, which means it is the modulus square of psi2, psi1. Since alpha, the scalar of a vector with itself is 1, we can eliminate alpha. We are left with this equation here. But this equation is true only for orthogonal states. What does it mean? It means that it's true only when psi1, psi2 are 0, or when psi1, psi2 is 1. Okay? So what does it mean? It means that it is possible to find I mean, it's a contradiction because psi1 and psi2 are not general qubit state, but are only orthogonal states. And orthogonal states are classical state. So basically, you recover the classical situation where you know that exists such machine that copies classical information. Okay. So, for example, if psi1 and psi2 instead are two superposition, this does not hold true, and this relation holds true only for classical state, only when psi1 and psi2 are bit. Okay. Let's go on. Do you have question about this one, about this part, about this proof? If so, write in the chat. It's pretty simple. Okay, maybe the way, the reasoning. Okay. So basically, you assume that it exists, but then you obtain something that is true only for classical cases. So okay, it's wrong, this assumption in the first place. Okay, since nobody is writing, probably it's all clear, or is not clear at all. But okay, I'm going on. Okay, let's start with quantum error correcting codes. Okay. So in general, so what we want to use is, considering the fact that we cannot copy quantum states, we want to use redundancy and entanglement and syndrome measurement to correct single qubit bit flip and phase flip. Okay, you can, in general, represent an error in your system, which is a phase flip or a bit flip, by unitary that happens with some probability p. So, okay, for some probability p, you get an x. For some probability p, you get a z. Otherwise, for probability 1 minus p, you get the identity, so you don't get the error. Okay. Are you okay with this? Please write something. Otherwise, don't know if there is someone or. Okay, at least someone is still here. Okay. Okay. Perfect. So okay, I'm going to show you now the 3 bits. Okay, let me. Why is it rather than face it by an arbitrary? Okay, let me briefly go back here. And let me write something. Okay, let me show you this. So one of the questions was about, okay. So at the end, so the proof stated that if you assume that you can do this, and with the same U, the same unitary, you can also do this. Where psi1 and psi2 are alpha 1, 0 plus beta 1, 1, and psi2 is alpha 2, 0 plus beta 2, no, beta 1. The proof states that if you assume this, then you get something that is, yeah, you get at the end psi1, psi2 equal to psi1, psi2 square. So when is this true? Okay, let me say, I can write this one. So psi1, psi2 is gonna be something like so. It's gonna be alpha 1, 0 plus beta 1, 1 times alpha 2, 0 plus beta 2, 1, which is again alpha 1, alpha 2, 0, 0 plus, so this term b1 alpha 2 give you 0 because the scalar product between 1 and 0 is 0. So we have plus B1, B2, which is 1, 1. So these are 1. This is again 1. If you do this squared, so you get this is equal to the modulus square. So it's basically modulus square of this alpha 1, alpha 2 plus beta 1, beta 2 square. So I guess that if you solve this, this is also equal to basically alpha 1, alpha 2 plus beta 1, beta 2 times the complex conjugate, which is alpha 1, alpha 2 plus beta 1, beta 2. So if you look at this, I guess that, okay, maybe this is not the best way of doing this, but I think that what you get at the end is that this equation is, so this equation holds only when, so alpha 1 is equal 0 and alpha 2 is different from 0, for example, or when alpha 1, beta 1 is equal to 1 and beta 2 is equal to 0. So something like this, I think. Something like this, I think. Sorry?
Hi, Ricardo. Yeah, thanks. Since I asked the question, thanks. Yes, thanks for doing this in detail. I understand the steps.
Yeah. Okay.
Okay. Maybe the deeper for this more or less is maybe unitarity. I guess if we allowed cloning of superposition, somehow this conservation of probability or unitarity would be violated, because that's what forces us basically to end up only on pure states to be cloned and never a superposition.
Yeah. Yes, exactly. But again,
unitary property.
As far as you are doing it in a quantum way, everything should be unitary. So everything should be unitary. So
yeah, interesting. Thank you.
Okay. Thank you for that. So I can go on probably. Okay. Then let me go here. So you can correct these two errors, let's say. One way is using this 3-qubit repetition code, so which encodes the qubit state, so of 0 into 0, 0, 0, and the qubit 1 into 1, 1, 1. And by measuring the state zeta 1, zeta 2, or zeta 2, zeta 3, so zeta 1 is, we're going to see what is this about. So zeta 1 is the zeta operator. So measuring these operators, the 1 and 2 or the 2 and 3 are referred to the index of the qubits. You can perfectly understand where the bit flip error happened. Okay, and this is basically the circuit that implements the correct the bit flip error. Okay, so okay, this and I'm gonna see it. I'm gonna explain this in step by step, but we're gonna focus on the 2-qubit case. So with 3 qubits are needed to perfectly understand where is the error, in which qubit happened the error, while mathematically I'm gonna show you just what happens when you have 2 qubits, okay? But then we will generalize easily. So consider, okay, this step-by-step analysis with just 2 qubit case, okay? The initial state is psi 0. So psi is your state associated to, qubit state associated to your quantum algorithm that you want to use in your quantum algorithm. First of all, you have to encode the information. We have seen before that we want 0 to become a 0, 0, 0, and 1 to become a 1, 1, 1. So what you do is by using this control not, control X. So control X, what does it do? Takes this, the initial state, alpha 0 plus beta 1 times 0, into the state 0, 0 plus beta 1, 1, okay? Which are also called the logical qubits, okay? Because I encoded this initial state into, I created the same state, but where basic states are just this one, okay? Which are called logical, okay? This part is about the error. So assume that we have a bit flip error on the first qubit. Okay, so bit flip error happens on the first qubit. So this means that with our state so far is this one. After this noisy channel, you get this state here. So, and this is a problem for us, for example, if our quantum algorithm works only with the state 0, 0 plus 1, 1, okay? So it's something that compromises our quantum algorithm, for example, okay? So what we're gonna do is we consider another ancillary qubit, an additional qubit, which is in the plus state. So we apply Hadamard to this qubit. So, and what we do, okay, the state at this stage is the state, initial state with an error, so the encoded state but with an error, plus the state of the ancilla. Then what you're going to do is apply a control zeta1, zeta2 operator. So in this case, we say that the syndrome measurement is associated with the operator zeta1, zeta2. And in fact, if you look at this, when we apply to our state control zeta1, zeta2, remember that this is the action of zeta on the 0 and 1 state. So you get a phase when you get a minus when the state is 1. The initial state, so the state that we have before the application of this control gate, becomes this one. So basically, you split this into 2 parts because, you split this summation here into the 2 parts. And because here, so when the ancilla is in 1, you apply the Z gates, Z1, Z2. Z1 and 2 here give you a minus sign that you can take out of the parentheses, okay? So after the Z1, Z2, you get this, the control Z1, Z2, you get this state. But again, you can rearrange the state this way, so you can, so the quantity inside the parentheses is the same, so I can rewrite everything like this. So okay, we have again another Hadamard gate applied to the ancilla. So the state of the ancilla is this one inside the parentheses, which is a minus gate. And we know that if we apply an Hadamard to the minus gate, what we get is 1. So at the end, we measure the ancilla. Measuring the state of the ancilla qubit, and if we find the ancillary qubit in state 1, we know for certain that there has been a bit flip error in the channel. So we had either psi or 0. So there was a bit flip error, but we don't know actually where. It was could have been the qubit 1 or the qubit 2. Okay, but we know for sure that there has been an error. And actually, we need 3 qubits in order to perfectly locate where the bit flip error has occurred. Why? Because in this, the first ancilla measures as like syndrome measurement associated to the first ancilla is zeta 1, zeta 2, as we have seen, while the second one has zeta 2, zeta 3 associated. So if the result of the first ancilla is +1, so which means that if the eigenvalue of zeta 1 and zeta 2 are +1, and the same happens for the other ancilla, which is in state whose eigenvector associated to zeta 3 is 1, we can conclude that no error has occurred. In the case where the first qubit is in 1, while the second qubit is in 0, you get an error in, we know that there has been an error between, in this block, so we know that there has been an error in either 1 or 2. But from this other measurement here, we know that there was no error between 2 and 3. So we know for sure that the error was in 1, in the first qubit. Same thing happens when we have the first qubit that tells you that there has been an error between, there has been no error between 1 and 2, and there has been instead an error between 2 and 3. So that's why we know for sure that the error was on the third qubit. If both of them give result 1, then the error was on the second qubit. Okay, so that's why we need it's a 3-qubit repetition code, okay, to correct the bit flip. Okay, yeah. Okay, these codes are the most famous code that can correct bit flip errors or zeta errors. In general, yeah, you can have also, I guess, phase shift of arbitrary angle, but then, yeah, this kind of circuit are not able to distinguish that kind of error, I guess. This is just zeta or X-like errors, okay? So in the other case, it's much more complicated. Probably you need much more qubits in the redundancy and much more measurements in order to detect something that is not zeta or X. Okay, it's yeah. These are the simplest error correcting codes, let's say, algorithms. Okay, let's also prove that when there is no error, actually everything works well. Assume that there is no error, so when UR is the identity, then after so the state left unchanged after the U associated with the error, which is the identity. So when we add the ancillary qubit in the state Hadamard is this part here. When we apply the control Z again, what happens is that the control Z in this case doesn't alter the state. There is no minus sign that came up somewhere, like in the case before. So this means that when we obtain H, we get this state here, which means that when we measure the state of the ancilla, we always get 0. So that's why when we get 0, we know that there has been no error. Okay. Is it okay so far? Please write in the chat if you want something. You want to know something more, or if it's not clear. Otherwise, I go to the next 3 qubit repetition code that corrects, that is able to correct phase flip, in the sense Z flip errors. Okay, nobody's writing, so I'm gonna go to the next slide. So it's phase flip error code. It's basically worked in a very similar way, but encoding your state, not in 0, 0, 0, but in plus, 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 and 1 in minus, 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 where plus and minus are, oh, sorry, here there is a typo. So, okay, does zeta1, zeta3 exist? Or no, okay. Here, zeta1 means just that, I mean, zeta I means that it is gate zeta applied to qubit I. So you can have also zeta1, zeta I, zeta3. It's just, yeah, but in this case, for this error correcting code, you don't need zeta1, zeta3. You works well considering a pair of qubits in the same order, so the same order of the drawing. Okay, but in general you can have it zeta1, zeta3. It's simply zeta1, so it's the gate zeta1 and the gate in zeta3, both controlled by the same qubit. Okay. So okay, for the phase flip is basically the same thing, but changing basis, which means 0, 0, 0 is this one, minus is with the, of course, with the minus in the middle. This time we do not perform control Z measurement, we perform instead control X measurement. I mean control X gate that we later measure in the ancilla. So basically it's exactly the same thing except for the encoding, which is different because now we are encoding into plus and minus state, and for the control. Okay. The nice thing is that about this code is that you know that what we said before, that you measure, so you acquire information about your state, but you never measure it. So after you find out which is the error, you can apply X here, or you can apply a zeta gate where the errors occur in order to restore the original state. Okay. So so this also covers the third part of the 3 points that we have: no cloning, bit flip and phase flip gates, and also measurement. No, because you're not measuring your state, you're measuring other qubits that have just some information about the error. Okay. Okay then. So this is the phase flip error correcting algorithm. Again, the initial state is this one. This state here is the one that encodes 0 into plus, and 1 into minus, minus. Again, here the analysis, we're doing the analysis for the 2-qubit case. Then, what does it happen here? We have the control not, the control X, which gives you this state, then the Hadamard that gives you this other state, okay, which is exactly alpha plus beta minus minus. Then we have the error, which is a zeta 1. So let's say that there is an error that is a zeta gate applied on the qubit 1, which the error changes the state in this way. Okay. So it's basically the same because zeta acts like X, but on a different basis. Okay. So X is the bit flip when the basis is 0, 1. Zeta is the bit flip when the basis is plus minus. Okay. So again, we add the Hadamard, the ancillary qubit with the Hadamard. We rewrite the global state in this way, and then we perform the x1, x2 control operation, which produces a minus sign in the ancilla, a phase in the ancilla, whenever you get the error. Okay, and again with the Hamiltonian, with the Hadamard gate at the end, you get this final state by measuring it again. And since you get, in case of error, you get you get the state 1 in the ancilla with certainty. But again, like we have seen before, you need 3 qubits. So you need an encoding into 3 qubits and plus 2 ancillary qubits to perfectly locate where the phase flip error has occurred. So as we've seen before, depending on the outcome of the ancilla 1 and ancilla 2, you know where if the error was in qubit 1, qubit 2, qubit 3, or there was no error. Okay. Finally, is the last thing that I'm gonna show you, the short code, which is a repetition code, but that can correct both phase flip and the bit flip. And the encoding goes like this. At first, one thing I forgot is to say is that you can correct both bit flip and phase flip errors using 9 qubits. Okay. So basically, how you do it? You encode. At first, you use 3 qubits to encode your initial state 0 into plus, or minus, minus. And then you add other 3 qubits for each one of the 3 qubits that you initially introduced. And you encode the plus, the 0 that appears in the plus as a 0, 0, 0, and the 1 that appears in the minus as, the 0 and the 1 that appear in the minus and the plus as 0, 0, and 1, 1, 1. So basically, what you're doing is this circuit here. So you first encode the initial state psi into the second, third, into the fourth, and to 5, 6, into the 7th qubit. So in this way, you get a plus, and the minus, minus. So it's basically what we've seen before. At first control and then Hadamard. And then once you've done this, you perform the other encoding, which is just control not encoding on qubit 2 and 3, 5 and 6, 7 and 2 and 3, 5 and 6, 7, 8 and 9 qubit. Okay. So this is a way of realizing this encoding. And by measuring, I mean by considering, like we did before, this kind of operators for syndrome measurement, so which are now, this is 1, 2, 3, 4, 5, 6, 7, 8. So I guess you have to add other 8 ancillary qubit to store the result of this measurement. And like we did in the other cases. And you can, by looking at the result of the measurement of the ancillary qubit, where there has been a control unitary associated to one of these syndrome measurements, you can detect where the you can detect both the phase flip and the bit flip, and where the error was located, in which qubit the error was located. I think, yeah, that's it for the error correction part. So we have 10 minutes for questions concerning everything we have seen today, or concerning error correction. So of course there are then more complicated error correcting algorithms, but okay, it's going beyond the scope of this introduction. Okay, it's going to be, there are codes, there are error correcting algorithms that are called surface codes, toric code. So there are different formalism that also take into account the how qubits are, so the topology of the qubit. So for example, if they are placed in a lattice, or okay, so depending on also on which qubit are connected to each other, you can also find different error correcting codes. So this is just the introduction. So the simplest one. Okay, so probably, yeah. Okay, yeah, these are, sure. Here, for example, here you can detect errors. So the ancillary qubits are used to detect errors, but then depending on the output, so if I know that there has been an error of some kind on, let's say, the first qubit, then of course I can correct the error, because I can simply apply, for example, here, I can simply apply the Z gate again to the third qubit. And then in this way, I, let's say, I eliminate the original error that was introduced in URZ. Okay, so I show you the detection part, of course, but then the correction it's easy. You just need to add some X gate or an Z gate. Okay, Okay. Are there other questions about also the thing that we have seen this morning? If you have, please write or use your microphone. Okay, what do you mean with the stretch? So I mean, for redundancy, I mean, I encode okay. You mean, I mean, these codes assume that the error appears here and that do not appear in the ancilla. I mean, okay. So yeah, if it's what you mean. Well, the redundancy is at this level, so where, so let me start with this. So the redundancy is here because I mean, you encode the state, the initial state 0 plus 1 into this other state. Okay. So in this sense, we have redundancy. Okay. Then, because what you want is to, so you have some probability of error. So classically, you do this because maybe the probability of error for 1 bit is p. Okay. But then if you encode the state 0 into 3 bits, the probability of getting an error becomes, let's say, lower because you have 3 bits. Here it is the same thing, okay? So by redundancy, so by adding more qubits and constructing the same state, you decrease also the probability of getting an error because yeah, that's the point of redundancy. Okay. Okay, perfect. Are there other questions concerning this part or the algorithm that we've seen today, this morning?
Just out of curiosity,
yeah.
In current hardware, what is the most common type of issues you have? Is it flip errors? Is it anything really? Is there anything you can tell us?
Well, I'm not sure, but I think in current hardware, the thing is much more complicated because probably the main source of error in today's device is environmental decoherence. This means also that somehow your quantum system gets so interacts with the environment, and the evolution when the system, the quantum system interacts with the environment is no more governed by a unitary evolution, but it's something that is called a master equation. So it becomes something completely different. And yeah, what people usually do is to in hardware is try. Right now, I don't think people are doing these quantum error correcting codes because it's very expensive in terms of qubits. But they're trying to do is they're running simulations that also take into account a model of interaction of the qubit system with the environment, and run the some algorithm, let's say, on the quantum hardware. And then they try to adjust the parameter of the simulation in order to better understand the model of the noise that they have on the device. Okay, so once you know the noise, then you can run a noisy, you run some algorithm with some noise, some noisy hardware, but then you can still reverse engineer somehow the correct solution. Okay, so however, nobody right now is doing these quantum error correcting codes so far. Right now, I mean, it's something that is going to be necessary in the future when we scale up to more than hundreds of qubits, thousands of qubits, if we want to run Shor algorithm or Grover algorithm. Okay, so probably, so yeah, it depends on the hardware. Yeah, the error depends on the hardware. So environmental decoherence usually adds, so there are phase errors. Yeah, you can, so you can have, for example, you can have, so you can model the interaction with the environment with something that changes the phase, or something that is called dissipative. So somehow, let's say the entanglement or superposition get lost in the environment. Okay, so you start with a large superposition, and after a while you lose parts of the quantum superposition, okay, in the environment, maybe, no? So it's a bit more complicated in the hardware rather than this. Okay, so probably this. Yes, some efforts right now is in the the mitigation of errors. So as I said before, we want to do as much as possible with these noisy quantum devices, which have intrinsic errors. So I mean, which have errors that we cannot avoid. So yeah, somehow try to subtract the noise that we know is going to happen. Yeah, and there are also some recent techniques that maybe use also machine learning to try to understand, estimate the noise in the device, and then try to, so, yeah, something like subtracting it in order to recover in order to take into account, yeah, the fact that you have this kind of noise inside your computation. Okay. Something else? Okay, are these is this necessary? Yeah, like we have seen here, in order to detect errors, you can do it, let's say, on groups of gates somehow. So you have zeta1, zeta2. So this block, let's say, is associated with the error inside this that may happen in the first 2 qubits. So is this the question? Yeah. So I mean, in these repetition codes, I guess, yeah, it's necessary to have this kind of gates. Yeah. Okay. If you want to ask something else, please write it in the chat or.
Would it be possible to have just a couple of articles, references on how to deal with noise, how it's done currently, how it's somehow modeled? I'm very curious about this. Is this modeled stochastically, or you mentioned machine learning, which is probabilistic. So.
Yeah, I mean that's what I know. Don't know much more about error correction than this. Yeah. But for sure, yeah, it's something at some point, if we are able to scale up to more qubits, you're gonna need this kind of algorithm that correct errors in order to run things that we know for sure have some kind of speed up with respect to classical algorithms. Yeah. I think we can stop now, maybe.
Yes, if there's no other questions, I say that we will see tomorrow with a lesson of quantum annealers. Okay, remember to sign up in the LEAP website if you want to use the annealer. It's not necessary, of course, but if you want, you can do it. And try to install the local environment with the instruction. If something is not clear, you can mail me. I will answer you. Okay? See you tomorrow. Have
Bye. Thank you. Bye.
Good evening. Bye-bye.